Morning, guys. Morning, Azra. Morning, Logan. Morning, Hike. Good morning, Ava. Good morning, Nikolai. Morning, Sammy. Hi, Charlie. So, you've noticed, hopefully, this morning, there is no DNA sheet posted. You are no longer doing them because they don't fit with what we're trying to do with distance learning. Plus, also, there's really only 3 main instructional days in a week now. It has been for the last couple weeks. So I would either have to do DNA XLs over and over or nothing. And while a lot of you did really well on the last DNA XL, that's not what the point was. So I don't want to have every 2 weeks a quiz. Alright. I just did that because it was getting close to the end of the year, and I wanted to have a quiz on that information. Alright? But instead, now we're going to double down on the assignments themselves. There's not really going to be a question to help you each morning. We're just going to kind of review a little bit here and there. Gravitational force in space, that is the next assignment. We are going to finish it tomorrow. So yeah, we're going to kind of fly through this assignment so we can get to the next one, which is about the Earth, the layers of the Earth, and how the Earth itself kind of compares to some of the planets we may have heard about. Alright. So today I'm going to introduce to you GFiS, or Gravitational Force in Space. There's a simulator attached to the Explore section. We'll take a look at it, and then we're going to answer the questions in the Explain section. And that's it, just the Explain section. The Extend section is only one question, and then the Evaluate, there is a table to fill in. And so we'll take care of that tomorrow. Alright? Fun fact number 1, so instead of DNAs, a little fun fact, there is enough DNA in the average person's body to stretch from the Sun to Pluto and back 17 times. All your cells, if you took all the strands of DNA and just stretched it out to a straight line, which it's not in your cells, it's usually all kind of, not tangled, but bundled, called chromatin. If you could stretch it all on a single line, it could go back and forth 17 times. That's insane. Also, it would make a line that would be microscopic, so that's pretty cool to think about. Alright, so gravitational force in space. I'd open it up if you haven't already done so and take a look at it. We want to get from last year thinking about this guy's idea of gravity. A blue whale's veins can stretch from the Sun to Pluto 2.5 times. That's crazy too. Thanks, Hayden. Found out a blue whale's heart can beat twice per minute at its lowest amount. Saw that the other day. That was pretty cool. Fun facts about blue whales. So we're trying to get away from this guy's idea of gravity, Sir Isaac Newton, in that just balancing of forces, gravity being a force. And we want to get into the idea, well, why does gravity make things move? How does it make things move? To this guy's idea of gravity, kind of over my face, Einstein, in the early 20th century, starting to talk about how space can bend and warp. And that would be the reason for why things move. Alright? So we want to get into the idea why the planets and asteroids and comets, everything moves in a curve and not in a straight line. Because on Earth we see it as a straight line. An apple falls from a tree straight down to the surface of the Earth. But in space things always move in a curve. Why do they move in a curve? That's what we want to get at. So, PhET gravity simulator. Take it to a link. It should, oh, it is Flash. I thought it was HTML5. So, I don't want to download Flash Player. You guys will be able to allow Flash. I might actually pull the simulator up on my Chromebook. So give me a second. In the meantime, allow Flash for the PhET simulator. I thought it was HTML5, which is a better version of simulators and use of sources online. Hi, Maddie. Screen share my Chromebook. Again, we're in here, clicking PhET Gravity Simulator, and you're just playing with it. Get used to how to use the different tools. I'm pulling it up on my Chromebook, not on my PC, because I don't want to download Flash, and my Chromebook can handle it just like yours can. Find a link, send it to me, Hayden. Hello, Rainy. Alright. That's good. Oops. Actually, I gotta double check. Because there's a couple of them. Make sure this is the right one. There we go. Alright, so I just clicked and allowed it to run. This again comes from here, PhET Gravity Simulator. PhET is a website that's run by the University of Colorado. They have different simulators there, different visuals, pretty cool. There's lots of different things to check out, but a lot of them deal with chemistry and physics, so we haven't had a chance to really use them this year. Alright, so that was the explore section, just kind of getting to this part, and not that, but this, and just running start to see what happens. I'll take Newton and my face down. Alright, just literally running start and observing, right? The purple object is just a smaller object, alright? The yellow object is a larger, massive object. You can think of this as a planet and a star, okay? Moving in a curve. Alright. Reset it. What if I move the planet closer to the sun? What happens to the orbit? Alright, so there's different things I can test here. Or I could change the angle. V means velocity, so how much velocity do I give it? Obviously shorter means less velocity, longer means more velocity. Whoops, my planet's gone. Alright, so there's different things you can do. You can play with velocity. Gravity is always present. You can't change gravity except for one way. And we'll explore that one way, or really two ways, as we get into this assignment. Alright, fun facts are just for fun, Rainey. There are no DNA sheets. Alright, so that was just kind of like the explore, doing a little bit of viewing, learning what the simulator does. Start by selecting the Sun and Planet preset. So up here in the presets, Sun and Planet. Well, it's just the default setting. Make some initial observations below. So it's kind of like what you were looking at in the Explore, and that's just running start. Make some initial observations. So my first observation is the purple object, the purple planet, moves in a pretty circular orbit around a star. Okay, the star isn't orbiting the planet. So, planet's orbiting the star in a roughly circular path. Okay, it's not doing a square, it's not going off into space, it's not colliding into the star. It's a circular path. However, at the same time, the star isn't stationary. It has a little orbit of its own. It's very, very tiny. You can see it right inside where the circle is. Okay? Right where the yellow star is. So, gravity has an effect on stars too. And yes, our sun would be moving in this pattern as well. Alright? If this is the Earth, this is the sun. Our sun is on a small wobble of going around and around on a tiny, 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 tiny orbital path. Alright? So you can make an observation about the sun, you can make an observation about the planet. Come back here. You can bullet some of those into number 1. Alright? There are 3 sections to the explain section, so 3 parts. Looking at the sun and planet preset, okay? Then investigating different variables you can change, alright? That's different settings. And then select the sun, planet, and moon preset, and then answer these questions. So, sun and planet, then looking at the different variables you can change, and then sun, planet, and moon, alright? And then that would be the entire explain section, alright? So, why do you think the sun, body 1, is moving slightly instead of staying stationary as the planet 2 orbits it? So I give you some kind of reason on why that yellow star is moving in a small orbital path. What could the reason possibly be? Notice it's locked with the planet. The sun is always on the other side of its orbit compared to the planets. As the planet traces, the sun's on the opposite side of its little wobble. Why? Maybe it's in the name of the document. And that's it, just for that first part. The next part's a little more longer, a little more complicated. Investigate the different variables you can change, answer the following questions. What variables were you able to change? So if I go back here, this one's not as obvious. I'm going to stop it. I'm going to reset it. Where can I change variables? Where can I change information? System-centered, I mean, I could do that, but that's not changing any variables in the system. Traces, grid, tape measure, that's just all ways to gather information. So where could I change information? There is a table down here. And there's three things I can change. I can change the mass. I can make the star bigger. And I can make the planet bigger too. I can make them the same size. I can make it slightly smaller. I can make the planet bigger. So I can change that right there. In the first part, it has a name. In the column, it's called what? Mass is one thing you can change in this simulator. Okay, so we can change the mass of an object. That's one of these. Oops. That's one of these variables. If I go back and then I use the other column names, I can come up with the other variables, right? And then Rainy's kind of ahead of me. Position and velocity. Okay? Those are the other variables I can change too. Now, when I click and drag the planet, watch the position box. Watch the position box for the purple. When I click and drag, it's changing X and Y. So you got to picture this as a massive graph, right? That's why they have show grid. 0, 0 is right here over the sun. So I can move it into 4 quadrants, just like I can do in math, right? So picture this as a giant Cartesian plane, and I can put the sun and the planet wherever I want. I can move the sun away and move it into different quadrants. So I can change the positions. Alright? Now notice the purple boxes for velocity. When I click and drag V, if I make the vector, the line, smaller, it gets smaller. If I make it longer, velocity is going to be much, much, much greater. Right? It's going to fly away really fast. Where if I just do it smaller, it barely moves and then they'll collide. Okay? So velocity is also something we can change. And I can even plug in like actual like numbers, like 100 this way and then 100 that way. Here, now I have a linear line, X and Y, right? If I make this negative, and I make this negative, I just did a reflection, didn't I? The sun can also have a velocity too. See that little gray circle? That's not there as a little design feature. That's the velocity's arrow too. So I can give everything a velocity. Here, I'll kind of do it like this then. Oh man, too much velocity. Moving too fast. So you can play with the velocity, you can play with position by clicking and dragging, and then you can change the mass by typing in a value. These aren't in grams, these aren't in kilograms, it's just units, okay, because this is a simulator. If you get way too involved in what you've changed and you don't know how to get back, just click. Well, click the preset, sun and planet. There. Reset, or if that doesn't work, sun and planet. And you'll go back to this. Alright? Everything goes back to default. So back into this chart, I am able to change 3 variables, help you answer this question, all right? Of mass, position, and velocity can be changed in the table near the bottom. Okay? So those are the 3 variables I can change, and these are going to become incredibly important because we're going to change these 3 to cause different effects, and then tomorrow at the very end, mass, position, number, and velocity, what action do you do and what effect do you cause is the final evaluation of this simulator, because the rules of gravity are plugged into the simulator, and we want to try and figure out what are the rules of gravity that Einstein kind of developed. All right? And yes, it depends on mass, its position, and its velocity. Okay? You can think of positioning as distance. So mass and distance, along with any outside force, is going to influence gravity. Okay? Is there a pattern that determines which object orbits around another? How could we answer this one? If I run start, the planet orbits the sun. Fine. Reset. What if I make the planet more massive? I have a binary orbit. 2 objects orbiting around each other, around a center point of mass. However, who has the bigger orbit? The sun. So if I reset this, maybe make it 600. The sun is still being affected by the planet. The sun goes into the planet. In reality, this would be not a planet anymore, this would be a star, right? So 2 stars almost, by this massive change. What if I give the sun velocity and the planet nothing? Gonna have to give it more velocity. Nope. Still colliding. Eventually, I should be able to get this thing to orbit around the other. There we go. So to make the sun orbit the planet, in reality, make the sun orbit a larger star, is kind of what happens. I have to give the planet more mass, and I have to give it more velocity. So is there a pattern? Well, if I reset this, I go back to sun and planet, I hit start, the planet orbits the sun. Before, if I make the planet larger, the sun orbits the planet. So whichever object has more mass has a greater control over the other object. So what's the pattern here? It's about mass. You could include also what happens with velocity. Because when you change an object's position and its velocity, like Jake Raney said in chat, you change that object's trajectory, its path, which is part of its orbit, which is affected by gravity. So position and velocity affected by gravity. So you can tell me the relationship with gravity. I would say it's a positive relationship with mass and gravity. Positive relationship with mass and gravity. So explain that to me further. If I increase mass, what do I do to gravity? If I decrease mass, what happens to gravity? What does a positive relationship mean with that? Number 2. You can't see 2 on your own. Sun and planet hit start. And you're thinking of a reason why the sun is moving in a tiny circle. That's what you're doing in 2. Why is the sun moving in a little circle? You're not sure why? Look for patterns, right? What pattern can we see here in relationship to the purple planet? Is it completely random where the sun is and completely random where the planet is? Or is there a relationship? Is there a pattern? The pattern is the planet, if I stop it, the planet is opposite the sun here. Okay? And then if I start it and then I stop it, the planet is opposite the sun, or the sun is opposite the planet. Is it because the gravity is pulling onto the planets, creating a sort of Caber style of orbit? I'm not sure what you mean by that. We're looking at the sun, right? So the sun is obviously pulling on the planet. But at the same time, the planet has mass. Anything with mass has gravity. The planet is pulling on the sun. It's just so much smaller that the effect is smaller. So if you saw this from the side, edge on, you would see the star going back and forth. We're looking top down. The planet is pulling on the sun is pulling on the planet. The sun has so much more mass that it has a bigger effect. Because, like we've kind of moved on to say, there's a positive relationship with mass and gravity. So 5, when the mass of the sun is changed, why does the planet's orbit change? Well, if you increase mass, what are you going to do to the sun's gravity? So this goes both ways. What happens when you increase the mass? What happens when you decrease the mass? Tell me what happens. Okay? Increase mass of the sun equals for the planet. Decrease mass of the sun equals what for the planet? Okay? what's going to happen there. So you can put it in your own words. If I reset it, if I increase the mass, make it much larger, what happens to that orbit of the planet? Does it stay circular? Does it move further or closer towards the sun? So does it stay circular? Does it move further or closer to the sun? If I increase mass, obviously I increase gravity. So what's happening to the planet? We're getting more elliptical, and the planet's getting closer to the sun because of the increase in gravity. Reset it. Just make sure I'm on that. Decrease the mass of the sun, and what happens to the planet? So decrease it now to, instead of 200, let's do 100. Oh. See you later, I guess. Is he gonna come back? No. I think it's gone for good. Let's reset it. Let's go to like 150. So again, what happens to the planet? Does it get further or closer? Does the orbit get circular or more elliptical? The reasoning why is, again, because of gravity. Less mass means less gravity, and so that planet is more free to move away from the sun. You even saw what happens if you drop it too much. If you drop it by 100, so it's only a factor of 10 greater than the other planet, that planet is gone. It's out of the solar system. But keep in mind, for every action, there's an equal opposite reaction. So Newton isn't wrong. He just didn't have the complete picture in the 1700s. The planet leaves, but the star gets pulled downward to where the planet was. So the planet still pulls on the star. The planet's gone. It's now moving through space without a star. We call that a rogue planet. But the star also got kind of pulled and yanked down and is now on a new path in its galaxy. Collection of billions of stars. So explaining to me what you see there. When the mass of the planet is changed, what happens and why? And I think you saw me kind of do that too when I was playing with making the planet almost like a star. Sun and planet, if I make the mass even smaller, if I make it like 5, cut it in half, or make it 1, we'll go back to what we were originally. There's not really much of a change there to really record it. Alright, but if we make it greater, go up to like 70. Oh, see, this is now going back to number 2. Why does the star look like it goes in a little circle? Well, greater mass means a greater gravitational pull. So if I'm making the planet bigger, right? I go back to 10. I hit start. The star is moving in a tiny little wobble. But if I go to 70, Now that orbit of the star is much, much more obvious. Okay? So the orbit got bigger for the star when the mass of the planet got bigger. Huh. That then goes back to this rule that mass has a positive relationship with gravity. The planet's gravity increased because its mass increased, which means it pulls on the sun more. Okay? And guys, if you have any questions as you're kind of working through these, work ahead of me. You can be behind me. You can always rewatch, rewind once this is done. But if you have any questions, go ahead and let me know. Seven, when the mass of the sun and the planet are equal, what happens? Okay. Let's make them equal. Well, they now have two equal-sized orbits, and they both orbit a center point. So they're orbiting each other, but they orbit this center point right in the middle of this, almost like this Venn diagram, if you want to picture it like that. Right in the center of the Venn diagram, they're orbiting there. All right? And if I had a planet going around it, I'd have the planet Tatooine from Star Wars. This would be a binary system, a binary orbit. See, I can add a third object. Make this 200. Pull this out to the side. We'll go this way, and let's hit start. It's a very unstable orbit, as I think it's not coming back. Too much velocity. Very hard to set this up, so while... Oops. Yes, I'm going to keep sharing my screen. Why Tatooine would be really rare in nature. Because there's a lot of little variables to make this perfect. You need the right mass, you need the right position, you need the right velocity. Any of these are wrong, you don't get a planet that orbits two suns. And I've had people, set up trinary and systems, and they've had set up a Tatooine. But the hard one to do is a quaternary system, which you can actually do. That was interesting. See how it just kind of orbited one of the planets and then was ejected by the other. So you definitely can have fun with this, but I want you to also stay on track with, see how easy it is to get distracted? Stay on track with what I want you to look at too. When the mass of the sun and the planet are equal, what happens? They orbit each other because they have equal gravitational force. We call that a binary orbit. Remember that mass and gravity have a beautiful positive relationship. They really complement each other. Always there for each other. Okay? So if you make mass equal, you're going to make gravity equal. So those are the first parts of the explain section. Explain section is kind of long, because there's a lot to do with all these little pieces of the simulator. All right. After that, it's really getting into just these next two questions. There's 9 total. Sun, planet, and moon. What do you notice about the moon's orbit? Why is it this shape? Change the moon's mass to 2. What happens to the Earth's orbit? Okay. So we're going to resettle everything. Sun, planet, moon. I hit start. It's like a little flower. So purple would be the Earth, blue would be the moon, and yellow is the sun. We're going back to the SEM system. All right. What do you notice about the moon's orbit? It kind of looks like it zigzags around the Earth. Why is it this shape? Well, mass has a positive relationship with gravity, right? Right. However, why does the moon orbit the Earth and not the sun? Because doesn't the sun have a greater mass? And doesn't more mass mean more gravity? So doesn't the sun have more gravity than the Earth? Why does the moon orbit the Earth then? So what do you notice about the moon's orbit and the shape? The moon, just observing what you see, the moon orbits the Earth when it orbits the sun. It looks like a zigzag because the Earth is moving while the moon is orbiting, or revolving, if you want to use old terms, right? So that's kind of like the answer for 8. The moon orbits the Earth when it orbits the sun. It looks like a zigzag, but we want to know, well, why though, right? Why not the sun? Change the moon's body, number 3, to mass, to 2. What happens to the Earth's orbit? All right, so maybe we'll come back to that point. Let's change the mass of the moon to 2. So down here, I highlight 0.001. I go to 2, hit start. Uh-oh. Let's restart that. So we're getting a little irregular right now, and eventually ejected. We lose the moon. So what happens to the Earth's orbit? Well, the Earth's orbit squeezes in. It goes a little further in towards the sun. But that's because the moon gets ejected. Why does it get ejected? Well, because the moon has a stronger gravitational pull and starts pulling on the Earth. And the Earth slings it out into space. Because as the Earth moves closer to the sun, it becomes faster. Again, you want to see that speed. The Earth picks up motion. And you can see it yourself. It's picking up a little more speed and is ejected. But again, why does the moon orbit the Earth instead of the sun? It's because we have to come up with an answer, and that's gravity weakens over longer distances. Gravity weakens over longer distances. The Earth is closer, so the moon orbits it and not the sun. So if you remember back a couple weeks ago, I got mad at students just Googling the DNA question. And they got back, different things. But I got Google's answer about how a planet's size is the square inverse law to its radius. They got things they had no idea what they were talking about. All right? So a square inverse law means that something loses energy over doubling the amount. So we say gravity is a square inverse law because gravity weakens exponentially the further you move away from an object. So yes, it's true to say that gravity has a positive relationship with mass, but then gravity weakens dramatically over longer distances. So you are pulling on the planet Jupiter, and Jupiter is pulling on you, but over long distances, the gravity between you two is basically zero. That comes from Sir Isaac Newton's definition of gravity. Sir Isaac Einstein says things move in a curve because space itself is curved, because mass curves space and time, because space and time are the same thing. So the literal fabric of space and time can be warped. And that's what Einstein eventually determined, this right here. So gravitational attraction was established by Sir Isaac Newton, and then Einstein built off other scientists, including Newton, to come up with this idea that space can warp, that it can curve in all directions. This is kind of like a 2D representation, but it curves in all directions, and then objects follow the curve. It's like a coin going down that thing outside of stores and grocery stores. You put a coin on it and it'll go around and around and around until it falls down the center. There's lots of demonstrations of this, but I just want you to focus on these questions, and we'll talk more about this tomorrow. We'll review each of these. All right? I had a question through Remind. Don't know how the sun is on the opposite side of the planet because of gravitational pull. Wouldn't they be on the same side? I don't understand why that happens. Paulie, the stream's going to end in a few minutes. Good morning, by the way. So we go back to that question, number 2. The student's unsure why they're opposite each other. So if I go back here and I go back to sun and planet, I hit start. Why is the planet opposite the sun? There. Why is it opposite the sun? There. 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 They're all opposite. Okay? Wouldn't they be on the same side? Well, you have to understand is one of these objects has an outside force. The planet has velocity. So gravity and velocity, when they work together, kind of like Rainey was saying earlier in the stream, you develop trajectory. So gravity is being pulled along this line right here to the sun, to the planet. Hang on a minute. There we go. So the sun and the planet, they're attracted by gravity on this line right here, right? See my cursor now? This force of velocity, go 45 degrees between them, and you trace a trajectory, right? They're not opposite forces, but they're at a right angle, right? And then if you go in between the force of gravity and velocity, you're going to develop a 45-degree angle. That's the orbit of the planet. So the planet is constantly moving in a 45-degree angle all the time. And because it's moving in a 45-degree angle, it's going to make a circle. Now, why don't they end up on the same side? Because as the sun pulls the planet pulls the sun, and they never reach the opposite side. They're trying to get to the opposite side, but because the planet has velocity, it's always going to try and get to the opposite side and then just miss and then just keep going around and around. So basically the planet is trying to fall into the sun, but it misses every single time and just continues to go around in a circle. It misses the sun because of that sideways momentum, that velocity. Okay? They don't reach on the same side because the sun is pulling the planet here. The sun's pulling the planet to this side where it is, but then the planet is pulling the sun at the same time. So at this point right here, the planet is pulling the sun to itself, and the sun's pulling the planet to itself. So the sun wants the planet on this side of the orbit, and the planet wants the sun on this side of the orbit. But because the planet's going sideways, they never get there. By the time the sun's on the opposite side to meet the planet, or the planet's on the opposite side to meet the sun, the planet's already gone, and they're just going to keep pulling at each other for millions, billions, trillions of years. So it's a very complex answer, one you're not expected to get right away, but it's something that we're going to build to as we finish this document, all right, especially in the evaluate section. When I try to increase the mass of the moon, it looks like the moon crashes into the Earth in my simulator. Well, how much did you increase it by, Downey? So if I do sun, planet, and moon, remember you're only supposed to change it to 2. Don't change it to anything greater. The teal box, the blue box for body 3 should be 2. It starts at 0.001. So tomorrow I will go over each of these answers more in depth with you. I've already helped you a bunch in certain questions, but do the best you can, have an answer. We'll go through these questions, and then you're going to finish up the rest of the document, because tomorrow there's only one extend question, and there's only a chart for the evaluate. And it's about looking at the different variables, because gravity is affected by different variables that we see in the simulator. Wednesday, you guys don't have any class, but if you want to revise something or you're missing something, you're going to have that done, because teachers have professional development. And then Thursday, we're going to start scratching the surface, getting into the Earth's layers. When I set the moon's mass to 2, it doesn't fly away like it did on your screen. Well, go with what you observe. Hiking down and go with what you observe. If it crashes in, well, that's because the moon has a greater gravitational pull. I may have played with this fast and accurate tab, which may, if I make it a little more accurate, maybe that'll make a change. So it slows everything down, so all the patterns are more accurate. It looks like it might crash. Oh, I don't know. The orbits definitely get more regular because they're both pulling on each other greater. Moon's orbit's getting a little more wild. So if you observe the other one that I saw, obviously the moon has a greater gravitational pull. Uh-oh. So now the moon's broken free and is now orbiting the sun. So again, distance plays an important role. Now the moon is a planet. You notice that big, wide swing though? That was in the Earth and the moon planet was in resonance. So now it's starting to get a little more elliptical. So each planet can kind of pull on each other a little more and make it a little more extreme. So whenever they're in alignment, they make the orbit a little more extreme. So play with the accurate and the fast slider because it may make a different effect. Again, if the traces get too much and you can't really see what's going on, you can uncheck it. And you can just kind of watch the motion. And then you can always put them back on. But in this case, the moon has become a planet and the Earth is now free of its moon. This is because the moon has a greater gravitational pull. Those two desynchronized, they deorbited because the moon was starting to pull more on the Earth and the Earth was pulling more on the moon. So the moon's orbit got more and more extreme because it's trying to pull on the Earth more. So, a little ironic, and that the moon was pulling more on the Earth and it broke free because it acted like a slingshot. In the other case, same idea, the moon was slingshotted out of the solar system because it was pulling more on the Earth. So in both cases, the effects are different, but in both cases, the moon is pulling more onto the Earth and it causes orbit to become more elliptical, more extreme. In both cases, it broke away from the Earth. However, one of them, this one right here, the moon broke away from the Earth at the point where it flew next to the sun and became a planet. In the other case, it flew away from the sun and out of the solar system. But in both situations, the same kind of process happened. The moon pulled more on the Earth because it had greater gravity, became more unstable in its orbit, and was slingshotted away from the Earth. In one instance, it was towards the sun. In another instance, it was away from the sun. You have the slider right in the middle. You can see the change in the Earth's orbit too, because it's not orbiting the same purple line. It's either moving a little in or a little out. Moon's getting a little more unstable. And now we have the moon planet again. Keep in mind, I am also screen sharing my Chromebook, and so there could be little lag in the simulator. That could be lagging accurate versus fast. So if you're not getting the same exact version of what I'm showing you, it could be because of that. Like, this is my Chromebook, but on my PC. So there's a little bit of lag involved. If you guys have questions, send them to me throughout the day. Work on them as best you can. We'll review and then do the extend and evaluate tomorrow. Okay? Hope I answered your questions the best I could. If I didn't, again, send an email, send a message to remind. All right? Have a good Monday. See you, Ryan. See you, Hike. See you, Logan. Adios, Rainy. Bye, Mr. Cat.